would like to welcome everybody here, all of you early goers. And we're going to be treated to a wonderful exposition here on sensitivity analysis by Emmanuel Borgonova, who's got a lot of experience. He's crossed the Atlantic a few times in his career, and he's now at Bocconi University, where he is the head of his departmental unit. But he's also possibly well known to you as one of the co-editors of the European Journal of Operational Research. So he has a lot of experience in terms of working with NASA, other governmental agencies, and instructing them on all the nuances and benefits of analysis of models and sensitivity. And as relating to him earlier, our colleague Saul Gass, in his work during the last part of his career, was a lot on model validation. And all of that involves a critical look at sensitivity. How good is your model? Test the inputs, how they vary, how the outputs vary. He's served on a number of decision analysis boards, international journals, and I'll close by saying he's got a wonderful book from 2017 entitled, appropriately enough, Sensitivity Analysis. And so he's going to lead us through both an overview and then zoom in on a particular application to show how these methods work. So thank you so much, Emmanuel, for joining us this morning.
Thank you, Doug, for the nice introduction. Thank you all for being here, and thanks to Informs for making this possible. Sensitivity analysis is sort of the subject on which I have been working since my PhD at MIT now 3,000 years ago, and so I have been working a lot on the subject and see applications in several fields, from some work together with DARPA up to climate change models. And the plan of the tutorial is to give an overview, especially on scientific models, establish the goals of the sensitivity analysis, and analyze some sensitivity analysis methods. As you will see, there is a plethora of methods. I will only have to illustrate a few of them, and I'm sorry I cannot cover all of them because of the time constraints. And I will try to have a practice session. Unfortunately, I was planning to use my PC with the software, but the connection is not working with the screen, so that practice session is probably going to be reduced. And I will give you some further perspective of research. Please feel free to ask questions anytime. The first part is really referring to what Saul Gass had also at heart in his research. That is the fact that in operations research we develop several models. Almost all our research is applied mathematics, which means there is some model either in the form of an optimization problem or even a simulator that is at the heart of the exercise that we do. If you take the definition of operations research from Informs itself, it says that it is the combination of analytics and models, so applied mathematics, to solve problems and support decision making. In the recent years, there have been a great entanglement also between what you call data science and operations research. So our models have been enriched by the plethora of models that come from data science and machine learning. So what are typical methods of operations research? This definition here, operations research analytics, this is the definition of the Informs web page. So it's our community defines itself. And if you look at that, and actually I think this was taken out by Bard. I asked Bard, can you tell me what is operation? He took out these keywords, which by the way I think are also on the website of Informs. So it's a mathematical optimization, simulation, queuing theory, statistical analysis, decision analysis, which is also the community to which I refer the most, data science and machine learning. All these are models, methods of operations research, and they all entail quantitative studies, so mathematical models. I'd like to start with the decision analysis process as envisioned by Klemen in his book, Making Hard Decisions, 1997. And this was related to how you structure well a decision analysis process. And you see the first step would be problem identification. The second is identify your alternatives, then implement a model, evaluate the alternatives through the model, and perform sensitivity analysis. There it's the last step, because sensitivity analysis at that point would be, okay, now you have decided that you act according to the model. So you say you go left. And how robust is the decision you're making? Is the model giving you the correct inputs? And then you see that there is this cycle there. If you're happy with the analysis, you go to implementation. If not, you come back, and maybe the model helps you in revising some of the other parts. The overall goal is then to use a model to make decisions. And so one of the beauty of sensitivity analysis is that it's sort of cross-disciplinary, because even in the management sciences, you have seen works using the DICE model of climate change, for instance, by Hong in 2012, for robust optimization of climate policies. And so sensitivity analysis is transversal. And then you can take a step back and say, well, okay, but what are we in the end doing? See that this is the famous, or I don't know, well-known, but very nice scientific triangle developed by the Vienna School of the beginning of the last century. And they said that the magic of science would be to have all three vertices of this triangle. That is, you have a theory that creates a mathematical model. Theory means theory intended in the sense of good, so axioms from which you can derive propositions. These propositions imply a mathematical model, and then the model describes a real-world phenomenon. We have had examples of this type of procedure in physics. Well, if, for instance, you remember the well-known movie also, My Friend Einstein, or something similar, in which the English astronomer decides to test Einstein's theory that the image of the star should be deviated by a couple of millimeters from their original position, because the light would be deflected by the light of the sun, or the star would be deflected by the sun. And it's not an easy thought, but the mathematics of Einstein actually led to calculate this deviation. The experiment confirmed the deviation. So you have everything. You have the theory, you have the mathematical model, and the real world. In several of our applications, especially the ones on machine learning, we do not have this theory part. You cannot have a theory of why people wake up in the morning and tweet something. It's probably impossible to get a theory that has axiom for that. And so if you read this very interesting chapter there, Fricks and Hartmann 2017, and there is also a very nice book, Saltelli and Di Fiore 2023, published by Oxford University Press. The chapter by Fricks and Hartmann is actually a chapter of the Stanford Encyclopedia of Philosophy about what is models in science. And the Saltelli and Di Fiore is a book called The Politics of Modeling, and it has to do on how you should structure models to support policy making. So the Fricks and Hartmann is particularly interesting because it's the, if you want, epistemological view of what is a scientific model, and they distinguish two types of models: models of phenomena and models of data. If we take our literature in operations research, we would find several models that can be seen as models of phenomena. Now, here I listed several in many disciplines. For instance, for COVID, the Kermack and McKendrick 1927 model, which is a system dynamic equation, the Sayre model that has been so much used in the past years. This is a model of phenomena in which you do not have really axioms that create the model, but it's a model in which the analyst uses some knowledge of the phenomenon to create this simulator. And there you see stochastic simulators, for instance. There is a beautiful review by Nelson, so discrete event simulators in operations research. The beautiful Harris economic order quantity model in 2023, that's also a model of phenomena. I don't know if you remember, 1913, Harris. If you remember what Harris does, but he says, I have in front of me a production line with continuous demand, with continuous production, then I assume that I have to stock material. He creates an objective function. Okay, there is not the theory for that objective function, but he creates the objective function, find the minimum, and the minimum is the famous economic order quantity. That's a model of a phenomena in the sense of Harris, in the sense of Higgs, and so this Stanford Encyclopedia. And then there you have other, so business plans, agent-based models, for instance. There is a review by the Mark and Page. They are all models of phenomena. Then you have models of data. Models of data are the models that we used here that we use in machine learning, the big data revolution. And there you have a different perspective. So the analyst does not decide, say, the mathematical equation, or at least he picks it from a closet of possibilities, a neural network, a super vector machine, and fits it to the data. So in this case, you have X, which is some variables of interest, nature and Y. This figure is taken from a paper published by Zhao and Hesti 2019 in the Journal of Economics, Business and Statistics, but it's an overall framework. So what you want to do is you have X, which is some variables you're thinking of. So you create a mental model for the problem, right? Because if you want to forecast weather, clearly you're not going to take information about how many people leave their house today, right? You will collect the appropriate variables. Then you believe that nature always links these variables to the target variable you're considering, so sunshine or not. And you think, we hope, that's a sort of a leap of faith, that this can be represented by a mathematical equation. It could be stochastic or deterministic, but somehow we can capture the relationship through a mathematical form. The only point is that for G, we do not necessarily use our intuition about the phenomenon. We take it from, say, a set of predetermined functions. So models of data are deep neural networks, random forests, gradient boosting machines, say any other name. Even linear regression can be seen as a model of data, right? Because there is no theory, but you try to have a form that fits the data that you have. All this leads to what is called the black box menace. I think it was the black force menace in the movies, but now we have this by, for instance, Begoli and Bhattacharya. They say that the issue is the absence of theory, which is what we mentioned before. So we miss one vertex of the triangle. And then you need to do uncertainty quantification and robustness analysis as essential steps if you want to validate or have a valid model to be used. The same is in a review by Guidotti and others in 2018, and also Saltelli in a paper in Nature Communication there highlights the importance of using sensitivity analysis, especially when the complexity of the models increases. In operations research, we already noticed the problem, and actually this is a very nice paper by John C. Little at MIT. The paper is now published in 1970 in Management Science, so it's a couple of years ago. And it's very modern. The title of the paper is Managers and Models, the Concept of a Decision Calculus. And Little goes on and inspects what happens when managers need to use models. Of course, this view is 1970, so it's a little different than nowadays. Nowadays, with the data-driven revolution, there is much more of an opening in the industry to accommodate models. We have all started several years ago, but there is, say, a flow. Our mentality is much more open. There, Little had really to open up also the mentality of the industry to be starting using linear programming, for instance. But one of the conclusions of Little was that a model runs the risk to be rejected if the manager doesn't feel the model as his own. Clearly, a manager will never have the competencies or should not have the competencies to build a specific model for a specific problem, but then you need a communication, okay? So you need something that goes from the model to the decision maker, and Little has this sentence: a process needs to start to find out what it was about the inputs that made the output come out as they did. And this is sensitivity analysis. So you need to understand why the model is giving certain predictions. And this you can only understand it if you vary the inputs. There are some quotes. I will go only for the second one. So the third one is by the Nobel Prize Samuelson, 1941, in a paper in Econometrica that establishes, if you want, 1941, sensitivity analysis for economics, which was then called the comparative statics. Maybe you have heard it under this name, and it was the sensitivity of equilibria. And the second one is funny, is a sensitivity analysis for modelers. Would you go to an orthopedist who did not use X-ray? So if we have to use a recommendation system, so we are taking a recommendation from a model, an algorithm, what do we do? So suppose your knee hurts and you go to a doctor and the doctor touches the knee and says operation. Would you trust the doctor? No, you say, could I please have an X-ray before we decide to operate? And then sensitivity analysis is this operation. So it's this. We want to do this, the X-ray of models before we want to use them. So this leads us to what are the goals of sensitivity analysis. First of all, if you inspect Scopus, the database with papers, and papers that have the word sensitivity in the title, you find something like 1 million results, but because sensitivity is a synonym of dependence, okay? So if I study the sensitivity of pressure to temperature in certain means, then okay, I have sensitivity, but that's not a sensitivity analysis. Instead, there are some works that do sensitivity analysis in a sort of model-independent or general ways. So these goals are the ones that I found in the literature, and that are sort of the similar questions that are asked throughout several works. The first is, but before I start, this is an interesting question by Percy Diaconis. Probably you know him. He's a professor of statistics at Stanford. And he has a very nice story. If you Google his Wikipedia page, the story is somewhat famous. He started with gambling. He abandoned high school to start with gambling, and then he said, well, but to be a good gambler, I need to study probability. So he went back to study and got a scholarship at Berkeley, I think. So there was a university in Stanford itself that noticed how bright he was, and then he has now become a very famous professor in statistics. And he asks provocatively this question in a paper of 1989, in which he says, what does it mean to know a function? Sensitivity analysis means to know our function. Our model is our function, and we want to know it. So he asks this, and then he continues, okay, if you look at this, what can you say about this shape? Not much, because it's not really easy. Even if we have the analytical form, we don't see how really this function works. And then he says, okay, if you look at it, you can say it's smooth. Probably if you put in the values on 0, 1, you see it's bounded, but you cannot know whether it's convex, if it's monotonic, if it's oscillating. You have some oscillatory terms there, right? So you don't know exactly how this function is going. So this is his provocative thought. So, and then he starts saying that you need to put this function in a computer, and then to use the computer to see how the function works. So then for us, the setup is exactly this. We have a set of inputs x. They enter our function g, which is obscure. So for us, we don't pretend to know the form of g. And then we have an output. In general, you have the vector of inputs x that, depending on the discipline, can be called differently. In economics, sometimes they are called exogenous variables. In machine learning, they are called features. Parameters, sometimes in simulation, if you want to resolve what is that, you could call them input parameters. Then you have our input-output mapping, and y is the vector of outputs, quantity of interest, and it's called a target, for instance, in machine learning. So in machine learning, when you have x and y, sometimes you talk about features and targets. The classical hierarchy model, if we want to write the formula of Harris, was Q star equals ms over c, where Q star would be your target, so the optimal order quantity, the quantity of interest. M is demand, S is the order setup cost, and C is the cost of placing the price of one item in the stock. So this follows the reasoning that Harris made in 1913 to derive this formula. In our general notation of before, how do things change? They become y equals root square of x1, x2 over x3, because now we do not attribute anymore a meaning to m. That is, we look at it just numerically, so we want to know how y behaves as a function of x1, x3, and x2 numerically. And then y would be the optimal order quantity, x1 is demand, x2, and x3. Okay, so now in the next notation, we will continue without having a specific meaning to the inputs. The first goal that many people use in sensitivity analysis, or they try to find answers to, is factor prioritization. That is, what is the most important input that drives the behavior of your model. In machine learning, this question is often called feature importance. Okay? In sensitivity analysis, sometimes you have the name importance measures. You can rename it if you want, feature importance instead of factor prioritization. And the goal is to find what is the most important input. And as we are going to see, the question needs to be structured because, for instance, one important aspect that you need to consider when you perform a sensitivity analysis is the scale. That is, are you varying your model around a particular point of the input space, which is like a reference scenario, and I move slightly, so I do a perturbation, okay, then you will have something that is important, but locally at that point. Or you may want to have a finite scale. So we do, like you will see later, a tornado diagram. So we do some scenarios and we change in a finite way the inputs. Then in that case, what we would have is something that is important but on a finite scale. Or you want to inspect Monte Carlo, your input space, then it's called global sensitivity analysis, because then you have a thorough inspection of the input space, so it's called global scale. A second important goal, which is the one that I think is more close to the Furbinger quote on X-ray, is interactions. That is, you want to understand whether your input-output mapping responds in such a way that it is additive, that is, each of the inputs has a separate effect, or if there are important interactions. So when you vary a couple of inputs simultaneously, then they are complements or substitutes. That is, if they are complements, then they increase each other's effect, or if they are substitutes, they annihilate. So if you are looking for edging, you would like substitutes. Otherwise, if you want to increase your profit, you want complements. Another goal is direction of impact, which means you want to understand whether the quantity of interest is increasing or decreasing in one or more of the variables. And also here you have several ways to answer this question, which is local scale, and then you use the sign of a derivative, or on a global scale, and then you would have to use some recent methods developed in machine learning, which are quite interesting to understand direction of impact in general settings. A last one, which is sort of, let's say, not trivial, but very well established, is stability. That in doing all of this, you also can understand the stability of your model, because you get a range of variation. And sometimes you also want to understand the regions where the model breaks. So you want to understand when your model is not robust to give you accurate predictions. So it extrapolates, or there are problems with the numbers. So now I'll go over the methods. I'll try to cover the main ones that I've seen, at least based on my experience. There are several others. It's not my intention to exclude them, but probably we will not have time to go through them. So first of all, the scales. Here is another plot that may help us in, let me see if I can do this. So suppose that you calculate your model, and for some choice of the inputs, you choose X0 as a reference scenario. For instance, if you are running a climate model, this could be a scenario of the IPCC. So they say this should be the base emissions, or it's the reference scenario. Then what we can do is find another point, another scenario. If this scenario is far from X0, then we would have a finite scale, so you have a finite jump. If the new scenario, the perturbation, is very small around X0, we would have a local scale, so infinitesimal, so a perturbation, a gradient. And if you want to inspect the entire box here, what we call the global scale. The differential sensitivity analysis, which would be what happens if we have a slight perturbation around that point X0, is based on derivatives. Okay, so nothing surprising. In fact, derivatives go back to Leibniz, and I also don't recall if it is 1654 or 1684. But if you Google it, you will find a page of Leibniz equations for derivatives, and you see that the notation that we are using is exactly Leibniz notation. So then if you use a differential sensitivity analysis, we are going back to the 1680s. Yes, it's true, but numerical codes came up when computer could have some speed. So first works that could apply differentials in a proficient way to computers are about the 90s. Okay, so the innovation there is how to compute gradients, and you know there is this also nice book on automatic differentiation by Grivank that tells how you can find derivatives directly implementing the codes. So while the idea dates back in the history, its implementation, of course, is new. For the EOQ example, if we use the gradient as a sensitivity measure, so we use the partial derivatives, what we would find is these three expressions. Okay, if we decide that our reference point is 213, okay, I inserted the numbers by chance, we would find that the optimal order quantity is 0.82, and the values of the derivatives are 0.20, 0.41, and minus 0.14. So if I ask you what do you make out of these numbers, the answer would be don't trust the magnitude. Okay? Trust the sign, because the sign says, all right, the x3 has a negative effect on the EOQ, because x3 is the denominator, which is okay. So if it increases, the EOQ decreases. The other two have a positive effect. But why cannot we use the magnitudes? Because derivatives in general are not comparable. They are on different scales. And in this case, it's true because I think the third variable is a cost. So you would have that the dimension of that derivative is derivative of divided by a cost. And the other two are just numbers, or no, also the setup cost. So you have two costs and one is a number. So in this case, 0.20 is a pure number, the other two aren't. Okay? So if we were to conclude that number 2 is the most important input, in this case we would be deceived by the fact that we are not considering the scale. So how can you remedy? You can, for instance, recombine these derivatives into a differential importance measure, which allows you to have general representations of local sensitivities, because it can be proportional to elasticities if you adopt infinitesimal proportional changes, or to derivatives themselves if the infinitesimal changes are equal. And it's something I introduced when I was at MIT. And it's assuming elasticity, and it is also nice because it's additive, so the importance of two inputs is the sum of the importance. So if you rearrange, so rescale the importances in such a way that they do not, so you take into account the difference in their units, you see that you get this result, 1, 1, minus 1. That is, if you now take the magnitude, they're all equally important, which is also somewhat intuitive because your model is just a product, right? It's x1, x2 divided by x3 root square. If I vary them by the same percentage, they should give me the same percentage variation, so they should have the same importance. And in fact, you get this correct result on the local scale. Scale, now, when you have stochastic simulators, okay, I don't know if you're familiar with this sort of distinction between deterministic and stochastic. The simulator has a deterministic response. If I fix the values of the inputs, it always gives me the same number. So the EOQ that we have seen in our example is deterministic. A discrete event simulation system or an option pricing system, depending on the parameters you look at, may be instead stochastic. That is, it gives you an entire distribution. So one of the first methods to do sensitivity analysis in that case was by Rubinstein, 1989, published in Operations Research. And the method is based on using the derivatives now of an expectation. That is, you summarize the uncertainty of your model, the distribution, into the expectation, and then you want to study the differentials of the local sensitivity for, in this case, sensitivity to the input parameters of the distribution. So these are the parameters of the distributions of the x's. And this has given rise to several seminal and important works in the literature of stochastic simulation with what is called perturbation theory. And you have the work by Glasserman, 1991, which is a book, and a review by Michael Fu, and other works with sensitivities not only of expected values, but also quantiles. So these are local sensitivities of expected value of quantiles by Hong, Fu and Hong, and several other value at risk and probabilistic sensitivity by this work. So this is a stream in stochastic simulation. On the other side, what you can do is you can test scenarios not only locally. So you've seen that now we were at the point because we were around x0. So what we did, we established the sensitivity around this point here. What people do is sometimes to place the inputs in some sort of ranges and say x0 is in the middle, then I decrease it by 50% and I increase it by 50%, or I move it by 20%. Okay, or you can assign a different variation range to the inputs. So your geometry will look like this. You will have your point x0, and then you have x plus, which is when you shift all the parameters to the highest values, and x minus, which is what happens if you shift all the parameters to the lowest value. And here I think Don will recall that this is the procedure to do the tornado diagrams that we use in sensitivity for decision analysis. So here are sort of my arrows that want to show you what happens when xi, one of the variables, is shifted at its minus value and its plus value. And what happens if you let the inputs undergo these changes? What you do is you inspect this hypercube, okay? But if you vary from x0 to x plus, you have this finite change, g at the point x plus minus g at x0, and you would like to understand why, to explain this finite change. So, for instance, for the EOQ example, if we have these ranges, from 1, 3, 0, 2, 2, 4, which are around the mean values that were 2, 1, and 3, and we shift all the points to the points x plus, we would get a delta G equal to 122, which is the new values minus 0.82, the old value, so 0.40. The nice fact about the sensitivity study here is that you can decompose the change. That is, you can understand exactly how much of this change is due to each factor individually, which is this finite change sensitivity index of order 1, first order effect, how much is due to the interaction effect, and the interaction is found how? You take the difference between the value when you change 2 of the inputs, okay, to the plus. So I move 2 inputs, I keep all the other fixed at 0. I subtract the individual effects, and I subtract the original value. So this gx plus minus gx0 is how much I have changed because I varied both of them simultaneously, and then I get rid of their individual contributions. So this is a residual contribution over the individuals, and this is the second order interaction effect. It's important to clean up from the individual contributions, otherwise you would not have the interaction effect, because you would have the second order change that contains both what happens when they vary by themselves and when they interact. So a tornado diagram is a graphical representation I attributed to Howard 1988, which is a paper in Management Science called Decision Analysis, Practice and Promise. And if you read the paper, it's quite interesting, especially about the name, because it said it was coined by a client. So he was supporting decision support to a client who saw the graph and said, okay, this looks like a tornado. For the EOQ, it's not a splendid tornado, but okay, you see that we have the factor which is most important now for the assigned changes, which is x2, goes up, and that it has the largest bars. The blue bar is what happens when we increase it, okay, so it leads to a positive increase in the EOQ. And here, otherwise, when you decrease it, it has a negative impact. When we vary x1, same story. So it means the EOQ is monotonical if you want to increase. So we know it's monotonically increasing, but it's increasing in x2 and x1, which is consistent with the equation, while x3 has a different thing. If you increase x3, you find a negative bar, and on the other side, you find a positive bar due to the fact that it depends, so it has a negative impact on the EOQ. Regarding interactions, we can decompose, okay, and this is exactly the finite change decomposition. I have the software subroutine associated with the tutorial. I'm sorry I cannot show it to you, but it takes really a second, it's very fast, to decompose the effects. These first 3 bars are the blue bars that you see in the tornado diagram. Okay, you remember the 3 blue bars. These other ones are the interactions. So they are how much is not explained by the individual sensitivities. If your model was additive, you would not have these residual terms. Okay, in this case, our model is smooth. It's small, it's a little model, so the interactions don't play a mega role. Pay attention also that if a model is smooth and you have infinitesimal variations, there is the tangent plane approximation that kicks in. And so interactions will not be important even if your model is convex. To see convexity, you will have to have some magnitude in the input variation. And in 2013, we generalized, in a paper in OR, we generalized the tornado diagram because there is here you go easily, I don't know if you're familiar with design of experiments, but if you want to get a complete decomposition, when you have 20 variables, you have 2 to the 20 terms, which is 1 million. Even if the computer is fast and produces them, it's a lot of terms to look at. So one simpler thing to do would be, well, I would like to have the importance of x1 summed to all its interactions. So I want the total contribution of x1 to the finite change, but I don't want to compute all these terms. And the same I want for x2, and the same I want for x3. This is possible because there is a trick in the mathematics, that is, if you move first the variables from x0 to x plus, and you move them one at a time, and then you move them, you start from x plus and you do the reverse operation. Turns out that the indices which are first order for going from the left to the right, when you come from right to left, they are also first order for that move, but they are the total so they contain all the interactions for the reverse move. So in two series of, so basically the same cost of a tornado diagram, you get also all the interaction effects. And this is what we present in the generalized tornado. You have 3 bars. This is the total effect of a variable. That is the sum of its individual contribution plus the interaction. I think red is individual, the green is the interaction, and this is the total. Okay. By the way, these are always cooperative variables, not always the case. Yes?
So, can the yellow bar be the interaction effect will
Exactly. That's exactly what I was commenting. In this case, we are sort of lucky they are all in the same direction. But sometimes you could have a negative direction that reduces the overall contribution. So by itself, it is strong, but when also the other variable varies, it diminishes the effect of this of your variable. So they are substitutes in that case. Thank you. And what would you get? So if we look at this graph here, what can we get? We get an idea of how important are the variables, which is the magnitude of the bars, of course, and I see x2 seems to be the most important variable. We also can understand what is its importance. Its importance is mainly individual, that it has a small interaction effect with the other one that contributes a bit. And but I also see a positive direction, which means that for this particular change that I have considered, x2 has a positive effect, the same as x1, and x3 has instead a negative effect, which confirms all the analysis that we have done up to now. So we can get a trend determination or direction of impact, what is the most important, and we can quantify the relevance of interactions and their sign. So the idea then, there is a set of really nice works that say, well, but okay, now you have done it between x0 and x plus. Can you somewhat sample 20 points and repeat the operation for the 20 points? Of course, that's a nice idea. It's a bridge between a local and a global approach, which is called in the literature screening methods. And I don't know if you have heard about screening methods in your investigations. In OR, we have 2 main screening methods that have been studied intensively. The first is the sequential bifurcation envisioned by Bettonville. I think it was in ISTIS, but 1995. So you have this sequential bifurcation method by Bettonville, and then developed intensively by Bettonville and Jack Kleinen in a series of works. The sequential bifurcation idea is you start with all your inputs, you divide them in a group of 2, then you perform a one-way sensitivity, you move them to a next level, the 2 groups, and then the group that has the highest effect, you continue splitting it into 2 till you find what is the most important input. The other method that has been also widely studied is the method of Morris, which has been, if I could say, has become more popular over time. And it is a method in which what you do is you randomize your main effects, so what we have seen before, at several locations. Morris has a nice way to construct the randomization. And then your statistics, your sensitivity measures are the average squared of the main effects, or the expected value of the main effects themselves. And it has been studied in Ankerman and Nelson. There are several works by Xi that recently generalized the way of finding the points also, because what people sometimes have in mind, so these are the effects. As you can see, they are Newton ratios, so they are finite change derivatives. There is some belief that these methods are computationally cheap, which is true, but if your model has a low dimensionality, because the cost of performing these calculations, even if you need not so many points for the model, may be high, because you need to find the sensitivity per input. So you have a sort of a conflict, or both the dimensionality of the model and the number of points, capital N, where you sample concur in the cost. And therefore, if your small n is already 1,000, if you have 1,000 inputs, the model, so the cost becomes already high due to the dimensionality. So an idea there is to go to methods that, in that case, so for high dimensional codes, do not depend on small n, so the number of inputs, but just on the number of points. That is, instead of investing 1,000 model runs to vary 1 factor at a time and get only 2 points in the input parameter space, what I would do is I sample 1,000 points, so same budget, but then I have a better coverage of the input space. This gives rise then to global sensitivity analysis, which is I want to have an uncertainty quantification. Now, you remember we assigned the ranges to the inputs. Suppose that we assign uniform distribution to the inputs of these ranges for simplicity, okay? You should assign distribution data-driven, but for the moment we are happy to assign uniform distribution to the changes. What actually would we get? We can do what is called uncertainty quantification, okay? So the quantification of uncertainty can be performed by usually Monte Carlo simulation. So you say run your model 1,000 times, or you run, so generate a sample of size 1,000 for the inputs, then you evaluate the model 1,000 times in correspondence, and what you would do, you do plot, for instance, the distribution of the EOQ, which is this blue line that you're seeing there, okay? So now we have an uncertainty quantification, so we can even talk about stability in a bit more of a robust sense, because we see that the EOQ would go from this very little number here that is 9, 10 to the minus something to something more, so 1.4, okay? So we know that our EOQ will not exceed, in any case, probably 1.5 or 1.6. You remember the base case was 0.82. This gives you an idea of how much would vary in our simple example. Here, I'm showing you something different. So the blue line is the distribution that you obtain if you just run your model, given the distributions of the inputs. So that's the, let's say, nominal view of our uncertainty. And here is the line that instead you would obtain, is the density that you would obtain if you know that x1 is equal to 2, okay? If you consider this new curve here, you now see that the expected value of y has increased, because you see that it's shifted to the right. So probably you will have an increase in the expected value. And okay, so your belief about the EOQ is slightly different than before. Do you agree? So if this blue is what I think about the possibilities that the EOQ have now, this is the marginal distribution of y. This is the conditional distribution of y, the red one, given that I have been informed that x1 is equal to 2. If some of you have heard of it, you are going towards a setting of value of information. No? This is exactly what happens if I gather additional information on an uncertain quantity. So actually, it's nice. One of the first works to propose, so once you have this data set, what do we have? We have actually a data set of input realizations, so features, and a data set of output realizations. So now Wagner, but also the literature on computer experiments says, okay, do the same as statisticians do. Now you look at your data as if they are synthetic because they have been generated by a simulator, but now you look at them as if they were data, okay, gathered from any experiment. And Wagner exactly proposes this approach in the journal Operations Research in 1995. And the title of the paper is called Global Sensitivity Analysis. The intuition of Wagner is to, okay, generate the input-output sample from an uncertainty quantification, post-process the sample, that is, you take the sample and you take out the statistical quantities of interest. And in particular, what he proposes is to find importance via variance-based sensitivity measures, which turn out to be Pearson correlation ratio 1905. This was defined by, this sensitivity measure there was defined by Pearson in a paper in 1905, where I will also show you his original intuition. And then why was not the Pearson correlation ratio used much more? Because it's difficult to compute. The algorithm to compute the correlation ratio is very easy to implement on a computer, but by hands it would have required several calculations. By the way, the correlation ratio 1905 is a amelioration that Pearson considered for his correlation coefficient that, as you know, instead dates back 1895. Okay, so then he said, okay, correlation coefficient does not capture linearity. In 1905 he proposes this. Then Wagner says the same thing, and this is in fact this first order variance-based global sensitivity measure. which in the same years is rediscovered by Ayman and Ora in a paper in Risk Analysis 1990, and by several works of Russian mathematician Ilya Sobol, who write these papers, and even in Efron and Stein 1981, this is a paper in Journal of the Annals of Statistics. So in different disciplines, they come back to the same results. I don't know how many of them cite back Pearson, but then someone also rediscovered that it was actually, originally the idea was in Pearson. But it's not important, but look at the years. 1995, Wagner is not citing Sobol or the others in the same time. Ayman and Ora, no, they're not citing Sobol. So this group of authors in different disciplines arrived at the same attribution methods or importance measure in the same years. So variance-based sensitivity measures since then have become quite popular. And to be fast here, I'm skipping some mathematics that is in the tutorial in the paper, but it's not here in the presentation. And one of the nice things about variance-based is that they are, so if we all know what is variance, so they give you the percentage of variance reduction if you fix an input, which is a great insight. If you see them as measures of statistical association, recently there has been a revamping of works with, for instance, a new correlation coefficient introduced in 2021 on Journal of the American Statistical Association by Chattery. If you look at these recent works, they highlight that these measures of statistical association should have important properties, especially when you apply them to data. And one important property that you want to have is this by Reny, that is, you want that the zero value of a global sensitivity measure is zero if and only if the output y is independent of your input xi. So it's a guarantee. Variance-based sensitivity measures are zero first order indices that you've seen before, are zero if there is statistical independence between y and xi, but the converse is not true. Because, I don't know, it's a bit technical, but you see that here we are taking the variance of expected of y given xi. If you have a model in which the expected of y does not change when you fix xi, and people have built a dozen of them in the literature as examples, you would find variance of that equal to zero, but not because the variable is inactive, only because it does not change the expectation.
Is the Rayleigh measure actually the Everlane measure of maximal correlation?
Right. Yeah, right. The Reny measure of maximal correlation is a measure that remedies this fact. So it is guaranteed to be
Stronger than that, because it deals with functional dependence.
exactly also. That's another property. I've not put it, thank you, Andrea. I have not put that in, but it's true. There is also another thing that you may want, which is functional dependence. That is, you want the measure to be maximal when you resolve complete uncertainty. I have not addressed it there, but for space limitations. But people have worked on that. So if you consider measures that consider the entire distribution, like the delta that you see there, then you have this property that it's zero if and only if y is independent of xi. These are other measures, okay, that are there. I've not written the one by Reny, also because it's a bit difficult to compute the maximal correlation coefficient of Reny, but it has the property that we wanted. In general, they can be all part of this common rationale, which is a distance between the blue and the red line that we have seen before. I'm skipping because it's a bit technical. And here there is also a nice connection that has been found in recent works that so this framework that you see, going from what is my marginal distribution and where would I go if I get information about xi, is close to value of information, which unfortunately is printed bad because of a font translation, but there should be an epsilon. And value of information, when you have a loss function, it's shown that if you have an appropriate loss function, for instance, logarithmic loss on densities would lead you down to a sensitivity measure which is in this framework here, and it is the Kullback-Leibler. So you can reinterpret several of these sensitivity measures as value of information under an appropriate loss function for a specific decision problem. It is reporting the mean, reporting the density. So how do you compete? Because we said we have a sample, right? So we don't want to do several loops of Monte Carlo iterations. We just have a sample and we want to find all this information from the sample. Here is the intuition by Pearson. Look at the quantity that we want to compute. We want to compute a distance between the marginal distribution and the probability, marginal distribution of y, but the conditional one given that xi is fixed. If xi is a continuous random variable, we have a problem because probability that xi is fixed at a certain point is 0. Okay, and then what is Pearson thinking of? He says, okay, take the scatter plot between your variable. This is really the scatter plot that you get out for the EOQ model with our uncertainty propagation. Okay, here they put probably 100,000 points, so it's blue. It's all blue, but there's several dots. Okay, and then he says, divide this into 10 partitions, or partition this into 10 sets, partition the support. Then, if you find the conditional density, look, the black one is our original marginal density. If you condition on the fact that x1 is in this bin, you get one of the blue lines. Now I have 10 blue lines because I've done 10 partitions. Then I can measure this distance 10 times from the blue to the black, another time from the blue to the black, the blue to the black. Okay? And this is exactly what Pearson is thinking in 1905. He says, find the conditional variance or the conditional expectation that given that you're here, the conditional expectation given that you're here, the conditional expectation given that you're here, and average them. This would give you his correlation ratio. Okay? But the idea of Pearson is that if I have many data, I can have very refined partitions, so my class condition, the condition that x is in a partition, is in one set of the partition, is actually very close to the condition being at a point. And I hope my next slide shows it. Here I choose 100 sets for the partition, and you see that now the bin is very small around the value of xi. Okay? Then you would say, okay, I want a guarantee that this actually leads me to where I want to go. And then the mathematics become a bit involved because you would have to prove that the sequence of random variables that you found by continue refining the partitions actually induces a sequence of distances that goes exactly to the value that you want asymptotically. You can prove it. Actually, it has not been proven by Pearson. It has been proven recently, and you need some properties of the distance in order to guarantee that this happens, but luckily, so it works. So the Pearson intuition works, and you can get out all these measures of statistical association from data using this partitioning approach. An alternative to that, which is probably also familiar to you, is nearest neighbors. Okay, so basically you fix a point, you find a sliding window. It's a cousin of this. Okay, here you sort of have fixed neighborhoods. There you have one point and you slide them to get the importance. Here, however, are some visual effects that are sort of nice. In fact, what you can do is, why don't we retain, when we do this computation, why don't we retain the information graphically and we actually visualize the conditional distributions, okay? So you see now here, which of these three variables, so you sort of could guess which of the variables is the most important from the behavior of the densities, because if you look, these densities here, they are nice, nicely colored, but maybe artistically this is the nicest picture of the three, but look at these densities are all close to the black one, you see? That they are close. Well, this one creates a lot of a mess, especially when it is in the left side, you see? Okay, so the black line now is much flatter, and there is a lot of variations in the conditional density, which means there is a lot of variation in what we think about the problem because we get information on that variable. So I would guess that the most important variable should be x2 in this case, and while these other two may have a similar effect. I don't know if I reported the values. So x2 is the one that, in fact, if you report the values of the importance measures, they confirm it. The delta importance measure and the Pearson correlation ratio, both of them would tell you that x2 is the most important variable, followed by x3, I think for x1 and x3, okay, or x1 or x2 of the converse. It's 3 is the least important and 1 is the second. I close with the other goal, which is direction of impact, and the question that we have is, does your model behave like this or like this? Which is a completely different behavior, because if you see this model here, okay, it's convex, but look at the lines, how they behave. They are all translations of this black line, Black line is the line of the average behavior, so you can still get out this information from the data, okay? Same sample. Now, the point is that because you have many scenarios, in each of these curves, each of these blue curve is what happens for one particular value of all the other inputs. So I vary mine, but I fix all the others at one of the possible values in the scenarios. So this one here is a one-way sensitivity function that is well known to people also in decision analysis, and it's part of the spider plots. I don't know if you have heard this name by Eschenbach, 1992 in Interfaces, okay, when the journal was called again Interfaces. And so what you see, the fact that they are all regularly translations means that your model is additive. So from this picture, you can also have an insight about interactions, because, well, in this case, something strange happens. You see that all three variables have a null behavior. So in this case, you would see them as non-important with, for instance, Pearson correlation ratio, because the conditional expectation would be 0. But the fact that you also are plotting these other lines shows that there is, in fact, the 0 is an average of the fact that they have positive and negative effects that are balancing. So here is the spider plot. Spider plot is, I fix all my other variables at the base case, and I vary only once the variable of interest. So this is the curve for the x1 in the EOQ. This is x2 in the EOQ, and this one is x3. As you see, x3 is decreasing, okay? But this is for one possible value of the others. What we have seen in this graph here will be several of these curves for several possible values of the others. And this is a spider plot. The global trend indicators are conditional regression curves. This is Wooldridge, 2003 is a book, popular book in econometrics. So in econometrics, this is like everyday day's life. And the partial dependence function instead of Friedman, which would be the black lines that we have seen here. This black line here would be technically this partial dependence function, which is defined in this way. And it's a marginalization over all other variables but mine. Okay, so it's not conditional, but marginal, so it's a different curve with respect to the conditional regression curves. Some final considerations. If we have to undertake a sensitivity analysis, what are steps that I would recommend or we should actually implement? First of all, not the same hammer for all problems. That's a wrong thing to do. Define clearly what is the quantity of interest. Second, do you consider uncertainty, yes or no? In some cases you cannot, because you don't have sufficient information to assign distributions. You want just to do some scenarios. Okay, then if there is no uncertainty, you are in sort of a local sensitivity analysis or finite change scale sensitivity. If you want to add uncertainty, you are in a global sensitivity. And then if you are in a global sensitivity, what is the statistical property of the quantity of interest that you are considering? The entire distribution, some quantile, its expected value, because depending on that, you may consider a different global sensitivity measure. Then once you have sort of defined the main settings of the problem, you can define the goal. What is my goal? Well, I want to understand the direction of impact. I want to understand importance. I want to understand the relevance of interactions. I want to understand stability. I need to use different methods, okay? And sometimes from a method I can get even 2-3 insights simultaneously. Then you need to ensure consistency between the first settings and the method that you are using. Select the method that is quote-unquote optimal in the setting that you are, especially depending on the cost of your simulator. When it's expensive, you may consider building what they call emulators. Okay, you have several sessions on, for instance, Gaussian processes for uncertainty quantification, even yesterday or today also in the conference. And finally, it results communication, that is, use a nice graphical representation to visualize the results to the decision maker, as they may not be confident with the methods, with the model. Insights for analysts. Why sensitivity analysis? Sensitivity analysis allows to validate your model, to understand how it behaves, and this in turn helps you in communicating to the decision maker, because the decision maker may have some ideas, but the model then, so you may even suggest what questions the decision maker should ask, or if he had some particular questions, you know what is the answer to those questions, and you can help the decision maker to ask better, be better informed given the results of the model. For the decision maker, sensitivity analysis is important because you don't want to trust the results of the model developed by the analyst immediately, okay? So you want to have some corroboration. And second, you also want to have answer to either stability questions or managerial questions. And the goals that we have seen should be a sort of first basis to ask the managerial questions, and this can then be enriched even by specific questions that the decision maker can have. Overall, sensitivity analysis allows you to use models in a more rigorous way. I really thank you for your attention for being here, and I thank Doug again for really, he was super kind in the entire process, and thanks Informs for making this possible. Thank you very much.
Well, let's thank our speaker for the wonderful talk here. And we have some time for additional questions, and so these will be recorded.
So, Professor, you know that, like, for example, there's a lot of like neural networks, and we have a lot of ways of calculating gradients using backpropagation.
Right.
I was wondering, comment a bit about how you would incorporate, like, for example, these days I can just calculate the gradient of any complex function using just a backward propagation pass and then figure out sensitivities. And I was wondering, there were two questions. One, if you could comment on it a bit on how it sort of integrates into research, but also whether it opens up other avenues of research or things that we could do now that we couldn't do before.
I think so I also thought sometimes on this, but then the fact that you have all the gradients, even when you do an optimization, you have the gradients. Okay, so that's a sensitivity measures for free, and it's actually randomized local sensitivity. So the question would be, why not using them? So why not exploit, so visualizing them or using them to get some sensitivity information, combining them in a differential importance. So yes, it's completely correct. The information is there. You just need to say what is the goal that they would answer. They could tell you about the direction of impact. You could think of some nice visual representation that would show you how the hyperparameters space behaves. And this is very insightful for black box models when, especially if you have many hyperparameters, you don't know anything about how, I mean, it should be important not only to get the result of the optimization, but also to try and see what happens inside the black box. Yes, so that's a good question.
Emmanuel, thank you for the very nice tutorial. So one question that I always have is how to deal with sensitivity analysis when you have multiple input parameters that are correlated with each other, right? So for example, if you think about the problem in energy planning, where you have a demand that is uncertain, you have technology cost that changes, and some of them, they are correlated with each other. What we usually do is perhaps perform some method of Morris, some tornado diagram or Monte Carlo sampling. But how to deal with that correlation aspect? Should we do design of experiments, and if so, how? How would you deal with that?
Thank you. No, the nice thing about what we saw with the data approach, so the data-driven approach, all this, is that the inputs do not need to be independent. So all these global sensitivity measures that we have seen, and even these functions that we have seen here, this direction, they are valid, the conclusion that you make even when your inputs are independent. This result about the fact that they are valid also when the inputs are dependent is very recent. But if you use this expression here, okay, and if you can calculate those ones, if your function, if your input-output mapping is monotonic, for instance in Xi, it remains, so the curve that you would get here would be monotonic. So you would, the indicator would reflect the intrinsic monotonicity of the model even when the inputs are correlated. You can prove it, even when the inputs are correlated. So it's a nice result of these modern approaches that have been developed to deal with machine learning data. So machine learning data are also correlated. So let's say the issue of correlation is in this case not a problem. It becomes a problem when you want to apply the functional ANOVA decomposition. So let's say if your mindset is I want to apply a functional ANOVA and I have correlated data, then the functional ANOVA approach would not work. But you can use these very recent approaches that would avoid that type of complication. Thank you. Thank you for the question.
I'll just remind people that it will be available up on the Inform site would be the technical paper that accompanies this, and also there is a beautiful volume that's available. I've got to check to see with Inform's publication, but this is a very nice thing to have in your bookshelf, so you can pull it out. This, in general, has many more references and more technical detail. So we thank Emmanuel for a really exciting
Thank
and
you very
informative talk, and have a wonderful day.
Thank you. Have a nice conference.